In this video, we will name ionic compounds, continuing on that topic, but we're going to start with naming ionic compounds that contain transition metals. And here things get a little bit different because so far we've dealt with representative elements where their charges are always predictable, they are always the same, and for that reason we don't have to indicate what the charge is of a particular compound. Now we're dealing with transition metals, and they are here highlighted in purple. And everything in this region, note that they all end in the B letter. Here the charges vary. So they're always going to be positive because they're always cations, since they're losing electrons, as metals do. But the numerical charge can vary. And because it can vary, we do need to indicate the charge in the name. Otherwise, we would have no idea what the charge on that particular metal is. So that's going to be the only difference in the naming process. We're going to use very similar ionic naming rules as we did before. We're going to list the cation first, then the anion, just like we did before. For naming cations, we're going to use the element name. And for naming anions, we're going to use the base name of the element plus the IDE ending to indicate that it's an anion. But as I mentioned, the transition metal charges vary, which means that we have to indicate the charge of the metal using Roman numerals. So you're going to list the cation name, then in parentheses, you're going to list the Roman numerals indicating the charge of that metal, and then the anion as usual. So let's review the Roman numerals very briefly. This is what they would look like. Most commonly, you will see 1 through 6 or 7. It's very rare to see anything above that. So if you're trying to focus on the most relevant ones, maybe knowing the Roman numerals for the first 6 or so would be most helpful. There are 3 transition metals that are the exception to the rule, and that is that silver is always a charge of +1. Zinc is always a charge of +2, and cadmium also always has a charge of +2. So with these three, we actually don't need to indicate the charge because the charge doesn't vary. For everything else, you want to include the Roman numerals in the name. So let's practice that. If we're looking at this first compound, the first element in the formula is copper. And just like with all of the other ionic compound naming, the first element just gets the element name, copper. The second element is chlorine. And as you may recall from the previous video, with the anion, we're going to change that ending to IDE. So we're keeping the base name and changing the ending to IDE. So that would become chloride. Okay, so this will be copper chloride. But as I mentioned, transition metal charges vary. So we don't know what the charge on that copper is. It could be 1, it could be 2, it could be 3. And because that can vary, we need to indicate that in the name. So in parentheses, we're going to use a Roman numeral to indicate what the charge on copper is. So that's the next piece of information that we have to figure out using the formula. And this is where it's important to know how that formula was constructed so that you can go back and figure out the charges. So there are a couple of ways you can do this. For most of them, you will be able to just uncross the charges to go backwards. So I'm going to take that formula. There's nothing after copper, which indicates that the subscript there is just 1. So I'm going to take that 2 and give it back to copper. I'm going to take the 1 and give it back to chloride. And keep in mind that metals are always positive, so that will be copper 2. Non-metals are always negative, so that'll be chloride with a -1 charge. The next thing you want to do is make sure that that actually makes sense. So look, you're always going to use the anion to frame whether these charges make sense, and because the anion charge does not vary, you can use it to figure out the charge on the cation. So I'm going to go back to the periodic table. I see that chloride is in group 7A. They all have a charge of -1. So that makes sense. Charge of -1 on chloride is reasonable, which means that the charge on copper was indeed 2, and we would call that copper 2 chloride. And we can just go back and doodle in the remainder of these representative element charges that we can use to figure out the charges on our transition metals. Okay, let's try another one. The first element here in the formula is chromium, so I will call it chromium. And then I'm going to leave in parentheses just a little blank space that I can fill in the charge of the chromium. The second element is bromine, and we're going to keep that base name and change the ending to IDE. So that will become bromide. Okay, that will be chromium bromide, and now I just need to figure out the charge on chromium. I can try using the same method as the previous problem. I'm going to give the 2 back to chromium. There is a 1 here that we haven't indicated because we never write the 1 in there. But I can take that back to the bromide and then just check if that makes sense. So that would give me a charge of +2 on chromium and a charge of -1 on bromide. I'm going to go back and take a look at bromide. And bromide is also in group 7A, which means it'll have a charge of -1. So that charge makes sense. And we would just call that chromium 2 bromide. So just keep in mind these charges that I'm writing in here, they only apply to transition metals. Sometimes students get a little overzealous and they include the charges on everything. Only transition metals do we need to indicate the charge. Let's try another one. Here the first element is iron, so I will write iron, and then in parentheses I'll leave a little blank space for the charge. The second element is oxygen. We're going to keep the base name and change that ending to IDE, so that will become oxide. So some kind of iron oxide. I'm going to uncross the charges and see what the charge on the iron would be. I can give the 3 back to iron, 2 back to oxygen. Keep in mind the metal is always positive, the nonmetal will be negative. And then I'm going to use the anion to check if that makes sense. So we'll go back. Oxygen is in group 6A, which means it has a -2 charge. So that makes sense. It looks like our uncrossing worked just fine, and we can call that iron 3 oxide. Okay, let's try this one. Here the first element is lead, so I will call that lead, and then in parentheses we'll indicate the charge of the lead when we figure that out. The second element is sulfur. Keep in mind that we're going to change that ending to IDE, so that will be lead sulfide. And then I need to indicate the charge on lead. So I can try using my uncrossing method. There's nothing listed after lead, so that would just be 1. And then I'm going to uncross my charges and see if that makes sense. So that would give me a charge of +2 on lead and a charge of -1 on sulfur. Let's use that anion and check if that charge makes sense. Sulfur is in group 6A, which means the charge on it is -2. So we see that that actually does not make sense. We cannot have a charge of -1 on sulfur, which means that the uncrossing method does not work in this particular example. So you may want to uncross because it does save some time, but if you always have to check the anion and make sure that these charges actually work out. And when you get into a scenario where it doesn't, we can use the following method. So I can give lead a little variable. I don't know what the charge on that will be. So I'm going to say, okay, well, the charge on lead is X. I have no idea. I'm going to figure that out. I know that the charge on sulfur has to be -2. And that just comes directly off the periodic table. It's in group 6A, has to have a charge of -2. Then I'm going to look at the subscript in the formula, and there are 2 sulfides in that particular formula. So I need to multiply that charge by 2 to account for the 2 sulfides. All of these charges have to add up to 0 because that's the only way that I can generate a stable neutral compound. And now that I have that set up, I can solve that equation. So x positive 2 times negative 2 will give us negative 4. And if we solve for x, that will give us positive 4, which means that the charge on lead was positive 4. And then I'm going to indicate that in my name. This method will always work to figuring out the transition metal charge, but it just takes a little bit longer. So I typically start by uncrossing and then I check it using this method if it doesn't work. The next one, I see that there are no subscripts after either of the elements, which means the subscript is just 1. So these are in a 1-to-1 ratio. But here we have to be careful because we know based off of the periodic table that the charge on oxygen is negative 2. And if we have a 1-to-1 ratio, well, that really means that the charges on this formula canceled out. So our charge on oxide was negative 2, which means the charge on chromium must have been positive 2 for these to cancel. The first element in the formula is chromium, so I will call that chromium. And we determined that the charge on chromium is 2, so I'll indicate that in parentheses. The second element is oxygen. We're going to change that ending to IDE to indicate that that's our anion, and that becomes chromium 2 oxide. Let's try one more tricky one. Okay, so here I also have chromium oxide, but the challenge is in figuring out the charge on the chromium. So I'm going to I can try my uncrossing method. I can just tell you right off the bat it's not going to work, but we can see why. So I'm going to take the 2, give it back to chromium, take the 1, give it back to oxygen. If I do that, I get a charge of positive 2 on chromium and a charge of negative 1 on oxygen. And looking at the periodic table, I can see that that is definitely not correct. The charge on my anion is definitely wrong. So we do not want to use the uncrossing method here. We're going to use the method to set up an equation like we did in this previous problem. Okay, I'm going to give chromium a little x because I don't know that charge. And then I do know that the charge on oxide is negative 2. And in the formula, the subscript is 2. So I have to multiply that by 2 to indicate that there are 2 oxides in that chemical formula. And the charges have to add up to 0. So if I solve that equation, x will be positive 4, which means we have chromium 4 oxide. Let's try one more example. Okay, so this will also be a chromium oxide. And let's figure out the charge on chromium here. So as you might have guessed from the previous example, this will be a more challenging example where we can't just uncross the charges. So I'm going to just give the variable x to the charge for chromium. I know that the charge on oxide is negative 2, but here we have 3 of them in the formula, so I need to multiply that by 3 to account for the 3 oxides. And then I'm going to set up the equation. And here, when I solve for x, the charge on chromium will be positive 6. So this would be chromium 6 oxide. The final part of naming inorganic compounds contains naming compounds that contain polyatomic ions. Here, the naming system is actually fairly straightforward. All you're going to do is name the polyatomic ions in order that they are listed in the formula. The challenging part here is actually memorizing all of the polyatomic ions and then recognizing them in the formula. So sometimes here students get thrown off because polyatomic ions, in some cases, these formulas contain only nonmetals, and then the students are tempted to name them as covalent compounds. So just be very, very careful with that. And here really the trick involves making sure that you have the polyatomic ions memorized and that you can recognize them in the formula. The actual naming system is not too challenging. So here, as usual, you're going to list the cation first, then you're going to list the anion second. Now with polyatomic ions, you're actually not going to change the ending. They're going to keep the exact same name. So the name of the polyatomic ion is the name that you're going to keep in the formula. And that applies to anions as well. So for example, if you had nitrate in the formula, you would call it nitrate. Do not change the ending. And this gets a little bit tricky because sometimes students confuse that nitrate ending to nitride. Or it's even worse with nitrite, for example. So that one letter can make all the difference. Nitrite is referring to NO2 with a -1 charge. Nitride with a D is referring to nitrogen with a -3 charge. These are very, very different scenarios with very different reactivity. So be a bit careful. That's kind of the challenge of these polyatomic ions. Every letter is important. The other thing to keep in mind is that with polyatomic ions, you do not need to indicate the charges, and you don't have to use prefixes to indicate the quantity of each polyatomic ion present in the formula. And the reason for that is the same as the reasoning for not including charges on representative elements. That's because they're always the same. So chlorate is always going to have a -1 charge. And for that reason, you don't need to indicate that. And you also don't need to use prefixes to indicate how much of each polyatomic ion is present because you can figure that out based off of the charges. So let's practice a few. As I mentioned, you're not going to change any endings. You're just going to list the name of the polyatomic ion. So here, the trickiest part is recognizing which polyatomic ion is present in the formula. And here I see NH4. If you don't have that memorized, that is the ammonium ion. Notice that it has a +1 charge. And that second ion, or the anion, is C2H3O2, which if you don't have that memorized, that is acetate. And notice that acetate also has a -1 charge. So this is why those charges cancel, and we don't need to indicate the subscripts of each one. Well, since the first one is called ammonium, and the second one is called acetate, that's the name of your compound. All you're going to do is list the names of these polyatomic ions and leave it at that. So that compound will be called ammonium acetate. Not indicating the charges, we're not indicating the subscripts, all is well. The second one, I see the anion is SO4. If you don't have that one memorized, it is sulfate. And notice that sulfate has a -2 charge. And that's where that subscript comes over here. So if you took SO4 -2 and you mixed it with sodium, well, we know that sodium has a +1 charge that comes from the periodic table. If you were to cross these charges, you would get Na2SO4. So that's where that subscript comes from in the formula. And all you're going to do is list the element name of the cation, and then you're going to list the name of the anion, which is sulfate, and that becomes sodium sulfate. So you do not need to change the endings here at all. This next one, we see that there is aluminum. If you were to look at aluminum on the periodic table, oh, my periodic table is so far now. Aluminum is in group 3A, which means it has a +3 charge. So here we are. Well, here's where things get a little bit tricky. Sometimes students see this subscript and they think, okay, well, is that 3 oxygens? What's going on there? And here is where it's really important to be able to recognize the polyatomic ion because this most closely matches phosphite. And notice that phosphite has a -3 charge. So what this is really saying is that we have one phosphite in the formula, but we're just not indicating that. And that charge on phosphite canceled out the charge of aluminum. So you would just call this aluminum phosphite. And if you're not clear that these charges canceled, that should be a -3. Notice that these cancel, so when you put that formula together, you just get AlPO3. Okay, notice when you have multiples of a polyatomic ion, it is included in parentheses. So this is telling us that we actually have 3 sulfates in a particular formula. You don't have to indicate that using prefixes because we know that based off of the charges. So here we have aluminum. I'm just going to call it aluminum. And here we have sulfate, which has a -2 charge. And if you want to go back, one way that you can check this is once you generate your name, you can go backwards, and I'm going to reconstruct that formula using my name and check if that is correct. So aluminum has a charge of +3. Sulfate is SO4 with a -2 charge. So if I were to cross those charges, the 2 would go to aluminum, the 3 would go to sulfate. But I have to be careful. This has to be included in parentheses. Otherwise, it looks like there are 43 oxygens in the formula, which is just crazy. And it looks like the formula that I generated exactly matches what we had. So aluminum sulfate is the correct name here. Here's another example with parentheses. NH4 is our cation in this case because it's listed first. So I'm going to go back and see, well, NH4 matches the ammonium ion. Notice that the ammonium ion has a +1 charge. So this is ammonium. And it is bonded to CO3. Notice that the ammonium had a +1 charge. So this too must have come from the CO3. And that matches carbonate. That's CO3 with a -2 charge. So I would just call this ammonium carbonate. And finally, here is a tricky example because this includes a polyatomic ion and a transition metal. Keep in mind that transition metals have a varying charge. So I'm going to start by listing the name of the element that appears first. That is chromium. And then in parentheses, I'm just going to leave a blank space for the charge that we're going to figure out from the chromium. Phosphate, I'm going to look at my chart and just figure out what the charge on phosphate would be. It looks like the closest thing that matches on this list is PO43-, which is phosphate. So it will definitely be chromium phosphate. And I can use my anion to figure out the charge on chromium. So I'm going to assign a variable x to chromium because I don't know the charge on that. And then I know that the charge on a phosphate is -3. Now I do need to account for how many phosphates are in the formula, and I see that there are 2 of them. So I have to multiply that by 2 to set up my equation. If we solve for that, we're going to get x is +6, which means this is chromium 6 phosphate. So that's the process for naming compounds that contain polyatomic ions. You're really just keeping the polyatomic ion name. And if you happen to have a transition metal, use the anion to figure out the charge of the transition metal. The other thing I wanted to review is, I know this list can be a little overwhelming in terms of getting all of these ions memorized. So there is some method to the madness here, and that is that the most commonly occurring polyatomic ion in nature ends in 8. Now, you wouldn't know which one that is without having it just memorized, but what I would recommend is for all of the ions that have families where you have the same elements, same charges, but the charges vary, not the charges, but the number of oxygens vary, notice that they all have the same kind of family name or the same base name. They're all based on that chlorine. So here, what I would recommend is memorizing the one that ends in 8. And you can figure everything else out based off of that one if you know the following trick. So the most commonly occurring one ends in 8. If the ion has one less oxygen, it ends in ite. So notice chlorate is ClO3 with a -1 charge. Chlorite is ClO2 with a -1 charge. Now, if the ion has even less oxygens or even fewer oxygens, so if ion has one less oxygen than the ite version, then we use the prefix hypo. So hypo meaning low. If you think about terms like hypothermia, means low temperature. So hypochlorite has one fewer oxygen than the ite version. This has only one oxygen, chlorite has 2 oxygens. And finally, if the ion has one oxygen more than the ate version, then we use the prefix per. For example, we established that chlorate has 3 oxygens. Well, if you have one more oxygen than that, you get perchlorate. So perchlorate has 4 oxygens in the formula, and it uses that prefix per to indicate that. So if you know those rules, really what you need to do is memorize chlorate right there. And based off of that, you can figure out hypochlorite, chlorite, and perchlorate. You can memorize phosphate, and based off of these rules, you can figure out phosphite. You can memorize nitrate, and based off of that rule, you can figure out nitrite. You can memorize sulfate, and based off of the rules, you can figure out sulfite. So that really cuts down on about half of the periodic table. If you know the rules, you can figure out a lot of these. The rest you basically just have to know, unfortunately. So here, making flashcards would be really helpful.